राहुल भाई, can you see the screen?
नहीं, full screen तो नहीं दिख रहा अभी भी.
अभी दिखना चाहिए. I don't know.
हाँ, ठीक है, अब दिख रहे हैं.
Okay, so actually because of some poor internet connection, sometimes it is getting delayed.
Okay.
Okay, so as I promised last week that means in my last talk, so I will be discussing some of my project what I am working on at IOP Bhubaneswar. So this is some unconventional critical behavior in this compound, lanthanum, barium, manganite actually. So we have actually substituted less of manganese to see the universality class difference or any sort of change in the quantum phase transition if possible. Hello?
Yes.
Okay. So good morning to both of you. I hope there is no one else. So today I'll be discussing some fundamental aspect of the quantum phase transitions, then some discussion on the synthesis, and followed by critical exponent analysis and the conclusion thereafter. So we all know what does it mean by phase transition. So phase transition is the transformation of one state of the system to another state of the systems with some drastic change in the order parameters. So the parameter, the external stimuli could be many things, but if you broadly classify the phase transition, so whatever phase transition occurs or happens in a given system as a function of temperature or just because of the fluctuation of thermal energy is known as classical phase transition. So let's suppose for an example is quite familiar one is ice converting into water, or ferromagnet becoming paramagnet. These are all very standard and these are known as a classical phase transition. However, if you study in more details, when people got to understand very seriously about the origin of magnetization, they finally got to realize actually it is not always classical phase transition which will dominate. Instead, sometimes quantum phase transition may dominate in a given systems, and in detail it can be studied very nicely by just studying its magnetization in a very particular region where actually order parameter diverges. So all these things actually originated from the Fermi liquid theory. So if you can see the diagram, first diagram, left hand side diagram, so you can see this is the classical critical region. You can see, so y-axis it is the temperature, x-axis this is the quantum tuning parameter or quantum critical point, QCP stands for. So if you see, if any sort of transition is occurring as a function of temperature, it is known as classical phase transition. Here you can see the 0 point energy or quantum fluctuation is much lesser than thermal fluctuations. Therefore, thermal fluctuation dominates. But here, if we see the quantum critical, where actually 0 point energy is comparable to the thermal energy, and the last one is the quantum de-Jadder phase, where actually thermal energy is much higher, much lower as compared to the 0 point fluctuation. So here I will be discussing on the magnetic phase transition, where so this is ferromagnet to paramagnet. You can see the very order state actually getting de-Jadder. However, in a small region there are still some order exists. Roll by 1 second. Hello?
Hey, okay. I was also about to say about that.
Yeah. So as I was telling, the nearby house, so
The signal to noise ratio is very small today.
Yeah, very small today. And moreover, many people are there because today is Sunday, so they are making noise because all are official fellow. Okay, so this is the order region and this is the Griffith region. Griffith region, as you say, these are the non-interacting cluster in a paramagnetic domain or matrix. Now, so this is the material which
Can you
actually
make
we
it
have
full
taken
screen,
for.
Kyanti?
Okay, yeah, I'm sorry, I did forget to do so.
Hmm.
So actually, this is the material what we have taken for the investigation. So the parent compound is lanthanum, barium, manganate, LaBaMnO3, where at the Mn site we have substituted the chromium and we have tried to see is there any sort of actually phase transition is occurring at the microscopic level. Of course, phase transition is always originate from the microscopic level only, but we have investigated it in more details, which I'll tell you. So LaBaMnO3, people have investigated and reported very recently that they have actually obtained a Griffith phase. Griffith phase means, as I have shown you here, if you can see my cursor. So this LaBaMnO3 actually a ferromagnet, but while it is becoming paramagnet after Curie temperature or after phase transition, there are still some region which are actually there are some spins which are clustering and they do not talk to each other. That means they actually arrange in a particular fashion. So, and they are forming the Griffith phase. So here we have actually substituted in chromium in place of manganese to see if any sort of interaction can be developed among the cluster, as a result of which there will be the disappearance of that clustering phase or a Griffith phase, and you may end up with long range ferromagnetic order. This has been proposed theoretically. And moreover, by the definition of quantum phase transition, it can be tuned by a minute change in the pressure at the atomic level in the unit cell of a given system, or by introducing a strain into the system, or by introducing a magnetic field. So we essentially have tried to introduce a long range magnetic order in the system and thereby try to disappear or try to set up a long range magnetic order in the system.
So,
Yeah, please.
if I may ask a question, so
Yeah,
will it have applications in making superconductors?
uh, it can have, but some people are saying actually, Rahul, you see that superconductor to exist, your system may not possess a strong magnetism because magnetism and superconductor doesn't like each other.
Okay. Not superconductors,
Okay.
but maybe
So
in making storage devices, data storage devices at
yes,
high temperatures.
in storage devices, in memory, as you said, memory devices, or if it can be actually forming a thin film or two dimension, it can be used in other spintronic devices. Okay,
Okay.
but as your guess suggests, or the way you have asked, since lanthanum, barium is and oxygen are there, so these are more important element in high temperature superconductor. So superconductor mainly people haven't realized it when the system exhibits a strong magnetism, but we do not know. Though 30 years, 40 years of research is there on high tissue superconductor, but people could not come up with a successful theory or experimental evidence on a system which exhibit high tissue superconductor. So maybe Cooper pair mechanism doesn't holds good there. So maybe we'll discuss it at the end. Maybe.
Okay.
So the synthesis of this material has been done by solid state reactions. Corresponding oxides or the precursors with suitable ratio have been mixed and ground thoroughly and put it in the furnace for few days at 1300 degrees Celsius. So something around a week. So entire processing may take around a week. And since it is a solid state synthesis, so you may have to have subsequent grinding and put it in a furnace. So and the reaction rate is very slow. So what you essentially need to do, you have to expose higher surface area for a long enough time, so that the effective reaction could take place in a more effective way, so that a single phase material can be obtained. So coming back to the magnetization study, look at the figure one. Figure one is It's a magnetization versus magnetic field, which we called MH plot in the first quadrant. And what is the temperature we have taken from? I've taken a range from 230 Kelvin to 290 Kelvin at a temperature difference of 3 Kelvin. Okay, figure A. Is it visible,
Yeah,
Ranveer?
it is visible.
Okay. So the second plot, figure B, is nothing but is known as arrow plot, or which is nothing but m square with h over m. Okay, m square with h by m. So what the analysis says, if you see, this is the TC, because where we have got the TC, let me tell you. Here is the empty plot, magnetization versus temperature. Since the transition is broad, I absolutely have no idea where the exact TC is. So what we have done, we have taken the first derivative, the inside is, okay, and which it is something around 260. Okay, this is 260. That is why you see this TC is nothing but 260K. But you see, as per this theory, Arrow's theory or plot, the MH plot or m square over h by m plot, the TC should actually make 45 degrees slope, or it should actually pass through the origin, making an angle of 45 degrees, which is not the case here. Okay, that means it doesn't really follow the mean field theory approximation. You can see this is nothing but the exactly replica of this, but here the coefficient of beta and gamma, if you place 1 by gamma, gamma is 1 and beta is 0.5, you can easily reproduce this plot, m square over h by m, isn't it? So it doesn't qualify to be called as mean field theory approximation.
Gyanti,
It is not for
is there a particular reason that you use the exponent as 1 over beta and not just beta, and 1 over gamma as not just gamma? I
yes,
mean,
yes.
why can't you just use them beta and gamma? Why use 1 over beta and 1 over gamma?
That itself the theory says.
No, that is okay. But what I'm saying is,
Yeah,
say
yeah,
you are using 1 over gamma in the x-axis and getting gamma equals
yes.
1, and beta.
No.
No, no,
But I am
let me finish my question. Let me
okay,
finish my question. So what I'm saying,
okay.
so and on the y-axis it is m to the power 1 over beta, and you're getting beta
Yes,
say 0.5. But what I'm saying,
right.
why can't you just use m to the power beta and get beta equals 2?
Now beta equal to 2, there is no such theory. There are several models. Beta is nothing but Rahul bhai, it's the variation of spontaneous magnetization. Okay.
Okay.
You see, okay, what I'm saying, if see this is the plot, if you actually draw the linear line and see where does it intersect to the y-axis, the theory of a magnetization says, or this arrow plot says, how can it distinguish between second order phase transition and first order phase transition? If the intercept, y-intercept is positive in m square over h by m plot, then it is known as second order phase transition. If it is actually negative, then it is known as first order phase transition. But we know magnetization is nothing but second order phase transition. Okay. But if you take 2, you do not satisfy to actually explain the magnetic phase transition, because as per the Arrow's theory, this exponent has to be less than 1. This exponent has to be less than 1. That beta.
No. Perhaps I did not ask my question properly. No, see, what I'm asking is, so it's one thing. So, okay, so let us replace 1 over beta by beta prime.
Okay.
Okay. So what I'm saying is, why use 1 over beta and get the value of beta to be 0.5? Why not just use m to the power beta prime and get beta prime equal to? I mean, why are we using 1 over beta? Is there a specific reason for using exponents only in the fractional form, 1 over beta, 1 over gamma?
No, that is just a mathematical trick. But the physics is this. Physics is The spontaneous magnetization variation or the beta is nothing but the critical exponent of spontaneous magnetization. Okay, it should not exceed 1.
Okay. So perhaps fine.
If it does, then it won't able to explain the second order phase transition. But what you said you can do for the simplification of the mathematics, you can play the trick and you can actually get that is a very good thing. But if you do so, then it will not explain this second order phase transition. It should not exceed 1. Okay, this should not exceed 1, and
Okay.
this gamma should not lower than 1. This beta should not greater than 1 and gamma should not be lower than 1.
Okay.
If it is, then there is something unconventional happening in the system. That's what the established model says.
Okay. Thank you.
So this is for the main field theory. This beta is 0.5 and gamma is 1. Okay. Likewise, this is 3D XY, and what we are essentially trying to find out by establishing different model is in which model you see the at TC, the MH plot is actually showing the linearity behavior or linear behavior. If you see, this is very much curvy nature at TC if you see. But look at the 3D XY model, look at 3D Ising, look at tri-critical, and look at the Heisenberg. You can clearly see more linearity is appearing here, is it not? Right? So it seems as if at TC, it is actually showing more linearity.
So what does it signify? Because as I can understand from this, you have used, let's say, 3 or 4 models and have fitted the data points that you have obtained from an experiment using all those 3 or 4 models. So what extra information is this giving me? That what I mean, so my first question would be, which model would you prefer? So let's say you have 3D Ising model, 3D XY model, and 3D some other model, Ising model. So is there a way of deciding which model should be preferred over the other?
Yes. So what I said, actually, the TC should pass through the origin. At a TC, the image plot should pass through the origin. That means, physics-wise, in a system, if it is actually Heisenberg, you know what is Heisenberg model is. Heisenberg model is the interaction between the spin wave function or overlapping between the 2 spin wave functions, and there is a direct correlation between the spins at different sides, and there is essentially long range magnetic order. But if it is 2D Ising, that means interaction between the spins in the 2-dimensional surface. Okay, likewise mean field is just an average. So, but here we could see none of this model actually satisfy our system. None of this model. And nowhere you could see the linear plot at a TC or MH plot at a TC making 45-degree angle to the origin and passing through it. Nowhere. Neither mean field, nor 3D XY, nor 3D Ising, nor tri-critical, nor 3D Heisenberg. But among all these models, 3D Heisenberg seems to be very nearer to the model where the system seems to follow.
No, I mean, so as you are showing me a lot of models, it's giving me a kind of discomfort to me. So I mean, so what we have in so let's say what my understanding is. So let's say in physics we try to explain, or for that matter in science, we try to explain as much as possible. We have the observation with as much as let's say if a physical theory is good if it can, if it has very small number of assumptions and it can explain a lot of observation. So my first question would be, you have shown me 3 or 4 or maybe these many models. So since it seems that there is there is linearity after some time, so there has to be some kind of relation between all these models.
Yes.
And or so in that sense there has to be some kind of I mean among these there has to be a model and others are perhaps a special case of taking various parameters in that model. Is this true?
You are right. You are right. Very right. You
So
are
so
very
which one
right.
is that model then?
This model is actually mean field.
Mean field. Okay.
This one, this one.
Okay.
This is the simplest among all and most familiar one. And then the most familiar one is 3D algebra.
Okay. No, you see,
Okay.
so what I'm trying to say, perhaps it's not related to what we do in cosmology. So
Yeah.
let's say you have, so I'll give you one example. So let's say
Okay.
you take dark energy parameter. I mean,
Okay.
not dark energy parameter, what it is called as the what it is called as it's W. It's divided. It's defined as the pressure density over the matter density. P over rho equals
Pressure
W.
density over
It's
matter
called
density.
as
Okay.
um, mm, oh gosh, I'm not able to recall the name. Anyway, so
Okay.
then you have some other cosmological parameters. So in one case, when you have the dark energy, you take W to be -1. Okay, that's one
Okay.
case.
Okay.
But and then you can also calculate other parameters. But then you can also vary W, and W can now vary. It can be -1.5 or maybe -0.5. But
Okay.
and perhaps though that model will give even will also give a better fit, but then because the number of parameters have increased, so I will not say that that's the better model, but then
Yes.
so let's say you have and there is a way of comparing two models. So at least
Yes.
this is what we also do in cosmology. That's the method of likelihood. So
Yes.
which method should be preferred over the other? So let's
Yes.
say you have model number one, model number two, you use the same data and you
Yeah.
and you use those model and get these plots. So
Okay.
so there is a method or maybe function likelihood that suggests that model one has to be preferred over model two. So do you also
Very
agree to the
nicely
same?
said. Yes, yes, yes. You are absolutely spot on. Means exactly that's what we have done, and we have actually to check the reliability. We are asking the question about the reliability of the model and the preference one over another. Is it
Yes,
not?
yes, exactly. Yes.
Yes, and that has to be within the error limit also. Whenever you are actually analyzing this many model, you cannot ignore the error
Okay.
analysis.
Yeah,
So we have done it.
but you have not shown the error bars in any of these points.
No, we are. I'll show you.
Okay,
We
fine.
are.
One second. So
Okay, it is not visible here since I
okay,
haven't given here. But remember, see this delta t as an experimentalist. Whenever we are actually setting up an experiment, the interval is 3 Kelvin, right? Here
okay.
from one plot to another.
Mm-hmm.
So whatever error will come, it should be less than 3 Kelvin. It cannot be higher than 3 Kelvin.
Mm-hmm. Mm-hmm.
Yeah. That thing we have fixed it in the instrument while measuring the data.
Okay. No, so since you will also measure H, you will also measure M. So and that will also have
Magnetism.
some kind of instrumental error or maybe some
You are right.
statistical error.
Yes. So that
So
also have been taken care of. That also have been taken care of.
I mean, so the thing is, this may not be applicable to condensed matter physics, but this is a very common practice in cosmology or high energy physics. So that's why I was asking.
Yes, I appreciate the question and it has enormous significance when you are actually showing some model fitting or some numerical analysis. You have to show what is the boundary of the error. There is no escape.
Yeah.
You are spot on. It's a very important question. And I'll show you whenever we have whichever data I have used or model I have used. I'll show you with the error and its reliability. That's what I have exactly done.
Okay.
So this is empty as I shown, and this is 5 quadrant MH. So the saturation tendency.
Mm-hmm.
Now, so which model is fitting, that I am not sure because none of these models seems to fit to my data because they do not show 45-degree angle with the origin, neither they show the complete linearity at a given TC. But remember, this is my reference. because this is experiment and no one can change it. This is fact. So whichever model will fit or the modified model will fit, that can be done. But I can do nothing about the experimental fact because this is what my system is. Okay. Now, this is my MH plot at 260 Kelvin because I show you this is my TC. So at exactly at TC, what is my MH? Sorry. This is my MH. Okay. So here we have actually fitted an equation and we have considered there is some linearity tendency here at a higher field. Okay. And inverse of that slope is nothing but 4.54 delta. I'll tell you what is the delta in the context of quantum phase transition. Okay, this is mentioned as delta, which is nothing but the inverse of the slope, 1 by 0.22. Okay, slope is 0.22. Now, so this is the Curie wise speed. You know what is Curie wise speed because it is paramagnetic transition, and after paramagnetic transition you can use this speed in a paramagnetic regime and see due to some disorder or defect is there any fluctuation, and we get 2.2 Kelvin due to some remanent magnetization and a disorder effect. And here the relaxation, how the magnetization decays as a function of time, magnetization dynamics. Now, yes, so I'll not go to that. I'll continue the story, and here it is. So this is the spontaneous magnetization at different temperature. You see, these black squares. What I have done, there is an equation called a modified error plot equation. Okay, so that has been fitted here. Okay,
and how do you get that? How do you get the MAP, modified error plot equation?
Yeah, that people have actually added an extra term to that error equation. If you can remember this, these are for the different concentration.
Okay, so let me also ask this question: Is this the modified error plot equation? Is this phenomenological, or can it be derived by using some principles of quantum mechanics?
No. It is phenomenological because it's a model, and people have you cannot derive it from the first principle. I do not know if it what is the first principle behind it.
Okay.
I don't know. I don't know. Oh, you. If I understood your question correctly, are you asking about how to derive this equation from the least action principle?
No, not the least action principle. So what I'm asking is, so let's say you start with some basic quantum mechanics, or since I think your system is not relativistic, so you will not get into the Dirac equation. So let's say quantum mechanics is applicable.
Okay.
So using that, can you get to that conclusion that M and H has to have this kind of relation, but whatever that MAP is suggesting? So that not from the least action principle, no.
Okay, not that fundamental. So I think it's a model dependent and phenomenological. I don't think it can be derived from the first principle as you are saying.
Okay.
I haven't seen if anybody has done. It's at least beyond my knowledge.
Yeah, I mean, so what I think is that at least they will, or they will at least give some justifications that perhaps error plot equation is something, and then you also said modified. So then they must have done something to the original equation.
Yes, that's what I'm saying. Here is the error plot, m square versus h by l. Because it is okay. Maybe next time I'll elaborately explain. But we have found here it doesn't qualify to qualifying to be the right equation to explain the system. Therefore, and see those black square we have obtained. What you do, you draw a linear line here and see the intercept. As I was telling you, the positive intercept of our equation will tell you, confirms you about the second order phase transition, right?
Yeah, that is okay. So I have one more thing. It's not a question, but perhaps a suggestion. So to me it seems that if these are the requirements, that at TC, that at temperature TC, plot between m square and h over m has to be a straight line that passes through the origin and having, let's say, slope 1. This is one requirement.
Yeah,
The second
yeah.
requirement is if you go above and if you go this red plot, so are these for smaller than TC or larger than TC? I think smaller than TC. Or sorry,
Which one? Which
let's
one?
say if you go above TC, so those plots are for smaller TC, I mean smaller value of temperature, T
Higher
greater
value,
than
higher value, higher value, higher value.
Okay, T larger than TC. Okay, so then
No. Sorry, Rahul bhai. This above equations,
uh-huh,
above plots.
uh-huh.
These are these are temperature below TC.
Okay,
That
okay,
means system is in order state, which
okay.
exhibits spontaneous magnetization.
Mm-hmm,
And
mm-hmm,
after TC is just down under,
mm-hmm.
which speaks about the inverse susceptibility.
Okay,
This
okay.
is spontaneous magnetization. This is inverse susceptibility.
Okay. So if I were to look at it completely mathematically, so let us for the time being, if I forget about the physics, so then my requirements are at T equals TC. It is supposed to be a straight line, and if the temperature is less than TC, um, the y-intercept. So if I draw tangent, so whatever the curve is, if I draw a straight line through the, let's say, the last points, then the y-intercept should be positive. But if the temperature is greater than TC, then the y-intercept should be negative. So
Yes.
uh, and given that it is also phenomenological, so there has to be a way. So perhaps it should not be very difficult to make a guess of what kind of curve that should be, that satisfies all these requirements. I don't think so. It should be
Yeah. It
that
is simple equation. Yeah.
it should not be that difficult. I
Okay.
mean, so because you are saying that all these models, and given that some of them are maybe these are not phenomenological. So it's not that difficult to come up with a phenomenological model that satisfies all these requirements, isn't it? So
Definitely
hasn't
not,
someone done
because
it
if
already?
you can see, yeah, because Rahul bhai, if you can see, these different models are nothing but the tuning of these two parameters, beta and gamma, nothing more. These are different value of beta and gamma, which are critical exponent of spontaneous magnetization, and another one is inverse susceptibility, nothing more.
No, but this is what you're getting from the by using the model, isn't it?
That is fine, but this beta and gamma value is fixed. That's what I am using in my experimental data. I have only MH, M and H. This is my experimental data. All other things have been derived.
Okay. Maybe I'm not getting the things right.
No,
You may continue.
you are correct. You are correct. I am just explaining your thing. You are correct only, because all those models are interrelated
Mm-hmm.
with some specific characteristic or feature they do not share, and there are something which they do share.
Okay.
It is just nothing but variation in beta and gamma, two parameters.
Mm-hmm.
Okay, so one thing what you get is the positive intercept of y and a negative intercept of y. And if you see, I'll go to the end. And Rahul bhai, please remember this part. This is my image plot right at the TC, and I have taken the inverse of the slope, which is delta. Okay. So now, so this is my positive intercept in the y-axis, and this is how it varies.
Mm-hmm.
And this is my negative intercept in y-axis.
Okay.
Or intercept in x-axis. You can see. So inverse susceptibility exponent varies like this.
Yeah, it will have
And
negative intercept on the y-axis. Yes. Okay, I understand.
yeah. So you can see how much TC we have got. So we are getting to 60.16 with error up to second decimal places. It's been given.
Mm-hmm.
So, but with the TC, the first derivative, what I have shown you, that is an experimental fact. Okay.
Okay.
This is the thing I have obtained by using some model and
MAP.
obtaining the intercept. Then I am trying to feed the modified error plot equation, and I am exactly getting the TC, which is very close to the experimentally obtained TC,
Mm-hmm.
which is
Okay.
fast reliability.
Okay.
And even if you are not, I'm sorry, even if one is not satisfied with it, because of there is some variation, there is some slope, then take the derivative. And here you can see, and you see how does it vary. Exactly, again you are getting to 60.92, again one up to 2 decimal places. And remember, as I was telling you, my temperature interval is 3K, right? Delta T. But you look at the error what we are getting, 1.23K. It is very much within the range. If you are getting error more than 3K, of course, that is an error which cannot be acceptable. But you look at the error, it is way below 3K Kelvin, right? So these are two reliability check. And now you see another condition is, so before magnetic transition and after magnetic transition, you know, at the phase transition order parameter diverges, right? So before phase transition, a system was in ferromagnetic state. The system exhibits a symmetric behavior in its critical exponent, and after transition, it also follow another trend. But at a TC, they should not be same before TC and after TC, which you can clearly see. Whatever temperature I have taken as spontaneous magnetization here, I have taken this plot. This epsilon is nothing but T minus TC by TC. Okay. At a given T, let's say 230K, and TC is my 260K divided by 260K. So what we have done, we have actually normalized. And if you see, this is a normalized equation, and I have taken the logarithmic plot, log, we got above T less than TC and T less than TC, they are actually two different universality classes. Okay. Again, that also further clarified here. This is normal. I do not know the what exact theory behind it, but they call it renormalization group theory plot. Maybe I have to look at the theoretical derivation.
Okay.
You see the way you see T equal to TC, they actually two are diverging. There is two different classes, a clear separation. Here you can also see T greater than TC is one way, T less than TC is another way. They are more or less falling one over another the way they are here. But at a T equal to TC, there is a clear gap, right? So that this 4 point quite confidently confirms absolutely there is second order phase transition, and they actually exhibit two different universality classes associated with the two different parameters. And what is the TC? TC 260K. Now, if you ask me the question, then you tell me none of your model is satisfied, as you said, because we have used the modified error plot equation. This is MAP stand for modified error plot. This KF stands for Cowl-Fisher. I am extremely happy, and it's an honor for me to say, because this Cowl is I know this person. He is a professor from
Ramesh Kaul.
SN Kaul happens to be a professor in I think happens to be a professor or a PhD scholar in IIT Kanpur.
Oh, okay.
And a faculty in Hyderabad Central University. SN Kaul.
Okay.
I think he's retired or about to, but I have met him, and so this is his equation, Cowl-Fisher model. So in order to just check whether the analysis is correct or not, so if you just look at this 4 point, then absolutely there is no ambiguity as far as the reliability is concerned. The analysis is very much correct. Now, if you ask me, none of your my model is fitting to my system, then you tell me which model it fits into and what types of interaction it possesses in the system. Actually, when we calculate, as I said, with the renormalization group theory, there is an equation. If you actually tune this beta and gamma, and there are other exponents what we need to derive parameters, what we have found, you know, the long range magnetic order is established or quantified by a term known as exchange integral, right? JR. That means how the interaction between the spin varies as a function of distance. So here we found Jr actually varies as a power of minus 1.85. And what theory says? Theory says if your system exhibit 3D Heisenberg, it should vary as a function of r to the power minus 5. If it
Okay.
is mean field, it should vary as a function of r to the power minus 4.5. But I am getting 4.85. That means above mean field, below Heisenberg. That means my system actually, after substituting chromium in place of manganese, the long range magnetic order is established, but it tends to become much more disorder and much more unstable and becoming short range. That means if you actually dope more amount of chromium, you may end up with cluster. You may end up with short range interaction where you may not get long range ferromagnetic order.
Okay.
This is quite unconventional, and this is that's what I am talking about for 1%. 1%. But here we have done for this is this one is always 0.5%. This is for 1%. And here you see the obtained parameter I got is this much: gamma 1.25, beta is 1.39. Okay, here it is. If you see, see if I plot those, how m over 1 by beta gamma h by m over 1 by gamma goes. You see, this is my TC 260K. You see how it is going. 247K, how it is going? Simply passing through the origin, simply passing through the origin, and the slope is 1, right? And look, it is quite straight. So this is what actually the correct model is, and for that model, my inverse susceptibility critical exponent is 1.25, and my spontaneous magnetization exponent is 0.39. Okay, this is for 1%, and likewise this is for 1.5%. So that for that value, gamma is 1.28 and beta is 0.36. So detailed investigation have been carried out on this system, and soon we are going to communicate it.
Okay.
And another critical point I have forgot to mention: the group who previously reported there is a presence of Griffith phase, just because of minute presence of chromium completely demolishes, means completely cancel, or we could see complete disappearance of Griffith phase with minute change in concentration of the manganese in place of chromium in place of manganese. So, and there are some unconventional variation of beta and gamma which would be reported.
Okay.
Thank you.
Okay. Thank you, Jyoti. So I already have asked my question. So Richard, do you have any questions to ask?
No, I don't have. Yeah, it was not easy for me to understand these things.
No, Rahul bhai is giving much more tougher cup than me.
Yeah, maybe because I can see it in some other way.